In this video, we're going to talk about another technique commonly used to find patterns in a number sequence. Let's look at the problem. What is the 100th term of this sequence? 1, 2, 6, 24, 120, 720. Clearly, we need to find out what is the pattern here. So at least we need to be able to write down the terms after 720. So again, like the other video that we talk about take a difference, in here we're also going to make a table writing down the index value and the term values, and we'll look at the relationships between the terms. So let's make a table here. The index, or write down the index, and the values of the terms. In the third columns, we don't know what that's going to be yet. So the index will be 1, 2, 3, 4, 5, 6, so the values are 1, 2, 6, 24, 120, 720, and so on. Remember in the other video, we said the common technique of finding patterns in a number sequence is take a difference. So here, if we look at the difference of 2 and 1 is a 1. Difference between 6 and 2 is a 4. Difference of 24 and 6 is 18. And this is 96. Well, this is not leading anywhere. There's no clear patterns going on here. So in this video, we're talking about a second technique called take a ratio. And let's using ratio R to represent the ratio between the neighboring terms. So what are the values of this ratio? The value for the first term is going to be the ratio of the second term and the first term. So 2 over 1 equals 2. And the value for the second term, it will be the ratio of the third term and the second term. 6 over 2 is 3. The third term is going to be 24 over 6 is a 4. And this 120 over 24 is a 5. 720 over 120 is a 6. At this point, it's very clear what is the pattern of this sequence. The value of the next term, 120, is basically the index value of this term multiply the previous term's value. So for after 720, the term will be 720 times 7. And the next term will be, let's say this value is 5040. The next term will be 5040 times 8. Okay? So we find the pattern is basically the next term will be equals the current term times the index value for the next term. So if we write down the relationship, V1, the value for the first term is 1. The value for the second term is the previous value times 2. The V3 equals V2 times 3. V4 equals V3 times 4. Can you write down the general term, the general expression for the term? If we take the recursive approach, let's just look at this. Actually, we can do two ways. So one way is V1 equals 1, V2 equals V1 times 2. So this equals basically 1 times 2. So V3 equals V2 times 3 equals taking the value for the V2, 1 times 2, and plug into V2. You get 1 times 2 times 3. And this equals 1 times 2 times 3 times 4. And this is kind of the plugging forward way. And you can get V, let's say 100 equals 1 times 2 times 3 times 4 times 100. Right? Clearly. The other way is going backward way is kind of similar. So V100, we know the V100 term equals the V99 term times 100. But the V99 equals V98 times 99, correct? And then times 100. And just keep doing this. V97 times 98 times 99 times 100. And so on equals V1 times 2 times all the way to 100. It also equals 1 times 2 times all the way to 100. Correct? So this is the general term for the 100th term of this sequence. And for any term, the term's value equals 1 times 2 times all the way to the term's index. Now I want to say a few things about this 1 times 2 times 3 times 4 times 100. We know, so we have this, the 100th term equals 1 times 2 times 3 times 100. You know, mathematicians are a bit lazy sometimes, so they like to invent some notations to represent complicated expressions. For example, for this expression, they invented something called a factorial, actually written as 100 factorial. So in general, any n factorial is defined as the number 1 times 2 times 3 times all the way to n. So n equals 100, it's always multiply all the way till 100. If it's a 10, it's all the way to 10. And this is called a factorial. And for factorial, n plus 1 factorial equals 1 times 2 times n plus 1, which equals n factorial times n plus 1. And this is recursion that satisfies for the factorial, and this is probably the most important relationship for the factorials. And then for the factorials, there are a lot of interesting problems people can ask. For example, a very common problem people ask is for n factorial, how many trailing zeros there are in a n factorial. For example, one problem goes for how many trailing zeros in the decimal representation or digital representation. in the digits. Let's say 100 factorial. When I say trailing zeros, it means that when I write down 100 factorial as a digit number, how many zeros ends this sequence? Okay, and this is a very interesting problem, and we can talk about this in a later lecture. That's the end of this lecture.